what's called the rational root theorem. Some people call it the rational root test. As you can read, it says if we have integer coefficients, then every rational root of the polynomial can be written in the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So what that's saying is that every rational root, that means a root that's not an irrational number, no square roots, and is not complex, has no i's in it. So every rational root has to be, every rational root has to be a component of your constant factors divided by your leading coefficient factors. So I'm going to get the words out straight. So let's look at how we know that to be true. Well, let's say that we have these two roots given to us. So if I've got these two roots, we can kind of work our ways backwards to determine what did the polynomial look like originally. So we know that if I move my 5 over and then move my 2 over, I'm going to get 5x plus 2. That was one linear factor. And I'm going to get 3x minus 4. That's my other linear factor. Well, if I put those together, just redistribute, I'm going to get 15x squared, and minus 20 plus 6 is minus 14x minus 8. So if this was my original polynomial, I can determine the existence of those two solutions based on what's going on here. Because how did I get this 15? I got this 15 by combining the first terms together. By combining that 5x and that 3x. So the denominators were factors of that leading coefficient. Well, how did I get the constant? Well, I got this constant by combining the constants from each leading factor. So that 2 and that negative 4, those numerators on our roots, came from being factors of that leading of that constant right there. So that's all that the rational root theorem tells me. It says to generate a list of possible rational roots. We're going to look at every way we could combine factors of the lead coefficient and factors of that constant. Because somewhere in that list, if there is a rational root, if there is somewhere that we cross the x-axis that is not irrational, then it has to be in this list that we're going to generate. So if I'm looking at this polynomial that we have right here, this f of x is equal to 15x squared minus 14x minus 8. And I didn't know that those were my roots. I could generate a list containing those by taking all the factors of the constant and dividing it by all the factors of the leading coefficient. That's the rational root theorem. So what are the factors of negative 8? Well, we have 1 and 8, plus or minus, right? Because it could be positive 1, positive 8, or negative 1, negative, or since it's negative 8, positive 1, negative 8, or negative 1, positive 8. So 1 and 8 are possible factors, and plus or minus 2, plus or minus 4. So that's all the factors of negative 8. Divided by factors of our leading coefficient. So 15 could be 1 and 15, or 3 and 5. So these are the factors of our constant divided by the factors of our leading coefficient. And we would then create a list of possible factors by pairing those up one at a time. Let's look at what that list would look like. So 1 over 1 would be plus or minus 1. 1 over 3 would be plus or minus 1/3. 1 over 5 would be plus or minus 1/5. 1 over 15 is plus or minus 1/15. Then the 2's. 2 over 1 is 2. 2 over 3 is 2/3. 2 over 5 is 2/5. And 2/15. And we keep going. We go through the 4's. So 4, 4/3, 4/5, 4/15, and the eighths. 8, 8/3, 8/5, and 8/15. Yes, that's very tedious to get those paired up, but as we can see, our actual roots, -2/5, showed up right there, and 4/3 showed up right there. So both of our rational roots in this scenario do occur in that list. And that's what the rational root theorem says. If I generate a list using this idea of factors of the constant divided by factors of the lead coefficient, if there is a rational root, it has to be in that list. So we're creating a list of possible answers, and then we go through and dig into this list to figure out which one of these are the actual rational roots. Well, how is it you think we could determine that these are roots of this polynomial? Well, we know how to do things like that. A root is also called a zero for a reason. It's what we got when we set our function equal to 0 and solve. There's two ways we can do that. One, I can recognize a root as part of a linear factor, and then I can divide with it, correct? So I can divide by this into this, see if I get that remainder of 0. Or what I can do is use this idea that this is the value that makes the function equal 0. It's kind of like the remainder theorem. Remember, the remainder theorem says if I'm going to divide by a polynomial or by a linear factor and get 0, that's the same thing as evaluating at that linear factor, and it should equal 0. But it says you get the remainder when you divide and you evaluate, you get the same remainder, but we're talking about a remainder of 0. So you can do it either way. Divide this into this, see if you get a remainder of 0, or the better technique, the one that goes a lot faster with what we're doing right now, is to take the function and evaluate it at, say, 4/3. And that will equal 0, right? 16/9 times 15 minus 14 times 4/3 minus 8 will come out and equal 0. So we go through, we do that math. Since it works at 0, we now know a factor. And it's just kind of how the rational root theorem turns into us being able to work. Because everything we've done to this point has been factor, 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 factor. Well, we looked a little bit in the last lecture with the theorems about roots of polynomials. And we said, well, if I'm given factors, then I can divide by those factors to get something small enough to factor. Well, if I'm not given a factor at all, say I have this huge fifth degree or quintic polynomial, and I don't know anything about it other than these are the coefficients, I do know first the leading coefficient, and I do know my constant. So from there I can generate a list, test the values within that list until I get one of them to give me a remainder of 0. Now I know a factor. Now I know a starting point. So from then, once we know a factor, we can divide to factor. And then just take it one step at a time from there. So that's the basis behind rational root theorem and how we're going to use rational root theorem. Give me a couple seconds. I will get a few examples up here, and we will start digging through and solving when we're not given anything other than finding roots when we're not given anything other than the actual polynomial. So here we have an example. We want to find all roots of this polynomial. Now I'll recognize that this polynomial is not one that I know how to factor just at first glance. Do a quick scan. Do we have a common factor we could pull out to kind of minimize our x's? You know, is there a common factor of x we could go ahead and pull out? Or is there a common factor just number-wise just to make our values or coefficients smaller and easier to work with? I don't recognize anything there. So we just need to go into our process. So the idea is I don't know how to factor it, so if I can figure out a root, then I can do some division and start factoring. So we figure out possible roots by doing rational root theorem. So we're going to do the factors of -24 divided by the factors of our leading coefficient, 3. Rational root theorem, factors of the constant divided by factors of the leading coefficient. So let's go through. We got 1 and 24 We've got 2 and 12. Need some more room here. Two and 12. I've got 3 and 8. And we've got 4 and 6. So that's the factors of our constant. Factors of the leading coefficient are just 1 and 3. So we create our possible list and do 1 over each one. So 1 and 1/3. 2 over each of them, 2 and 2/3. 3 over each of them, 3 and 3 over 3 is 1, which we already have, so we don't have to repeat that one. 4 over each of them is 4 and 4/3. 6 over each of them is 6 and 2, but we already have 2. 6 over 3 is 2. We already have 2, so we don't have to rewrite that one. 8 and 8/3. Let's do 12. And 12/3, which is 4. So we don't have to rewrite that one. 24 and 24/3, which was 8. So that's all of our possible roots as we go through. Now, we just have, it's a guess and check, just test them. Now, more times than not, it's going to, if we were to write all these out in order, it's going to be closer to the middle than it is towards the ends. It's just the way the tendency goes with polynomials. But we go through and we just test a few of them. We test them either by plugging them in or test them by, plug them into your function, see if they give you 0, or test them by synthetic division, see if they give you 0. I'm probably going to test with synthetic division right now just because I don't have my calculator right here to be able to punch all that stuff in. Synthetic just makes the numbers smaller, easier to work with. So let's just pick any number up here. Let's say we picked the 4. So if I did synthetic division with a 4, okay, x minus 4 would be the root, but 4, or x minus 4 would be the factor, but 4 would be the root. So if I go 3, 16, 27, 10, negative 24, bring down my 3, 4 and 3 is 12. Add 16, I get 28. 4 and 28 is 80, and 4 is 112. Bring down my, add that up, I'm going to get 139. 4 and 139 is 400. 440 is 160 minus the 4, 146, so 5. Just want to bring that 556, I believe that is. That's going to give me 566. So 4 times 566. 4 and 5 is 2,000. 4 and 6 is 240. So 2240 plus 24 is 2264, which gives us a remainder of 2240, or somewhere thereabouts. So as you can see, 4 did not really help us out at all, correct? We didn't get that remainder of 0, so we know 4 is no good. So we would just dump 4, try the next one. I get the idea that just based on how that one worked out, I probably need a negative somewhere in there, because when it was positive, the numbers just kept getting bigger and bigger and bigger and bigger, and they didn't, teeter back and forth and then eventually cancel out. So I would think that maybe a negative would be a better try. We can try it with negative 4 now. So we know positive 4 was no good. Try it with negative 4, bring down the 3, that's negative 12. 6 and negative 12 is positive 4, gives us negative 16. So the numbers are staying kind of manageable. 27 and 16 is negative 11. So that's going to give us positive 44. Nope, positive 11. So negative 44 and 10 is negative 34. So negative 4 and 34 is 120, 136. So again, we're not going to get the remainder of 0 we're looking for, get 112. So that tells us that even negative 4 doesn't work. And it's really a tedious process. If you've got the calculator, it's a lot faster to just punch 1 in for all those x's, see if it gives you 0, punch -1 for all those x's, see if it gives you 0. So you go through, you keep testing until you get to, let's go with 2/3, because I'm pretty sure that one does work. All right, so let's try 2/3 out. Bring down the 3, multiply, you get 2, that's 18. 2/3 of 18 is 12. 27 and 12 is 39. 2/3 of 39 is going to be 26. 26 and 10 is 36. 2/3 of 36 is 24, which gives us our remainder of 0. So I have the benefit of knowing what the answer is supposed to be, but you just go through and keep testing. We see that 2/3 was one of our solutions. It was one of our roots. So we've got x equals 2/3. There's the first one. Fundamental theorem of algebra tells me there's got to be 4 of them. But the good thing is we've done our test and our division at the same point, same part we did. So I'm left with this new polynomial, 3x cubed plus 18x squared plus 39x plus 26. Remember, 4th degree divided by 1st degree gives me 3rd degree. And we want to now factor this one. This one I do see a common factor of 3 I could pull out of that, and that comes from having a rational factor there that we're working off of. So 3, that's x cubed, 6x squared, 13x plus, nope, it's not going to, what am I missing? Oh, 36, plus 12. From here, I just do some analysis. X cubed plus 6x squared plus 13x plus 12. So in this one right here, it's a cubic, it's got 4 terms, so I ask, can I factor it? So will this one factor by grouping? Well, if I check it, x squared comes out and leaves me x plus 6. There's nothing I can pull out of these two to leave me x plus 6. So factor by grouping won't work in that case. So I have another polynomial that I cannot factor. So we just go back and we start the process over again. But the good thing is, if it's a factor of this, it's got to be a factor of this. So really it's just a modification of our original list. Well, we already knew the plus or minus 4 wasn't going to work. So let's just kind of go through and knock some stuff out. X cubed, my lead coefficient is no longer a 3, it's now a 1. So anything divided by 3, we can dump, because we don't have that divided by 3 anymore on here. We already, the one that had the divided by 3, we already pulled it out. Anything that has, let's see, we can only go up to 24, or we can only go up to 12. So 24 is gone, and 8 is gone, because those are not factors of 12. Correct? 1 and 12, 2 and 6, 3 and 4. So anything with an 8 or a 24, we can now dump. All right, so now we just kind of start the process again. If the 2/3 had been able to be there, so I don't even have to check it this time because I can't divide by 3 in this one. So the 2/3 only shows up once. If it had been in this second list, we could have tried it again. Remember, multiplicities do occur, so the same root can be used multiple times. But we're just focused on this new list. Go through and test. I believe it is -3. Yeah, so we'll just jump to it just to not waste your time. So -3 should work. So -3, 1x cubed, 6x squared, 13x plus 12. Bring down the 1, multiplies -3, gives us 3. -9 gives us 4. -12 gives us remainder of 0. So we get remainder of 0. That tells me that -3 works. So -3 is another one that works. And we could have grabbed -3 at the very beginning here, and then we'd have got the 2/3 right here. So the order you find them in is not going to impact anything. We still would have ended up with x squared plus 3x plus 4. That is something small enough to work with. We recognize it doesn't factor, but we can still solve it by quadratic formula. So -3 plus or minus square root of 3 squared minus 4, 1, 4, all over 2 times 1. So we get -3 plus or minus 9 minus 16 is -7 over 2. So to write it in complex form, because we've got the imaginary there, negative 3 halves plus or minus square root of 7 halves I. So that is our last two. Those are our last two solutions, or roots. So we can see 1, 2, 3, 4 roots for a 4th degree polynomial. Rational root theorem got us started, broke it to get us a list of possibles. We then divided by those possibles until we got a remainder of 0. Once we got a remainder of 0, we took that new polynomial, tested to see if it would factor. It wouldn't, so we just start the process over again by modifying our list of possibles. We got a negative 3 from that. It gave us a new little quadratic, which we didn't have to test anymore because we know how to solve quadratics, whether they factor or not. All right, 2 more examples I want you guys to do, so if you'll give me a second, I will get those up here for you. Okay, here's the example I want you guys to do. Take a couple moments, pause the video, take a crack at it, and I'll wait right here. Okay guys, hopefully you were able to get this solution right here. Let's go through and kind of talk about what happened. First thing we do, there was no factors overall, common factors we could pull out. So we then set up our possible rational roots. So factors of the constant over factors of the lead coefficient, pair them up one at a time. Then we go through and just start testing them. Negative 3 ends up working, so when I do my synthetic division with negative 3, I see a remainder of 0. And I'm left with this polynomial right here. Now this cubic is different from the last one where we had to go through and modify our possible roots list and start the process over again. This one actually will factor by grouping. So x squared comes out of the first 2 terms, leaving you 2x minus 3. 5 comes out of the second 2 terms, leaving you 2x minus 3. So that 2x minus 3 is your common binomial, and you're left with an x squared plus 5. From there, it was set each factor equal to 0, x equals 3 halves, x equals plus or minus square root of 5i. And we can see that we got negative 3 from testing our rational roots, and we got 3 halves and plus or minus 5i. That's plus or minus square root of 5i. That's 1, 2, 3, 4 rational roots for this quartic polynomial. So that's rational root theorem. Said I was going to put 2 examples up for you guys to try, but I'm going to say one of them we'll do it when we come into class tomorrow because it's got a lot of little things in it I do want to talk about in person with you guys. That's rational root theorem, and I will see you in class tomorrow, guys.